Hello everyone and welcome to Calculus. Today we're going to be looking at area under curves and something called RAM, which stands for Rectangular Approximation Method. So a train moves along a track at a steady rate of 75 miles an hour from 7 a.m. to 9 a.m. What is the total distance traveled by the train? This is not challenging math for you in calculus. So he goes for 2 hours at a rate of 75 miles per hour. 2 hours times 75 miles per hour. So the hours cancel and you get 150 miles. That might be one way you thought of it. You might have thought of it as almost a unit conversion, the hours canceled. Some people know the formula. Distance is equal to rate times time. So that's what I did. I did his rate, 75 times time, not even thinking about the units, but that will always produce the distance. Today, I'd like you to think about it in terms of a graph. So I'm going to graph his velocity over time. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I don't really know what this train does the rest of the time, but I do know that between 7 and 9, he's going a nice constant rate of 75. Now, what's interesting is that if I make a rectangle underneath this, the area of a rectangle is length times width. In this case, that length is velocity, and that width is time. Velocity is also known as rate. So this area is the rate times the time. This area is the distance. So here's the super exciting thing that we're learning today, is that if you have a velocity graph over time, the area underneath that graph will tell you what the total distance is. Now, of course, the chances of something going completely constant like that are very slim. The chances are that the train was going a certain velocity, slowed down, maybe it had a little hill or a curve it had to get through, and then it sped back up, and then it slowly increased its velocity until it reached that 75 and stayed stationary for a while. So the question we're going to ask is, how do we get this area? How do we get the area under an unknown curve? Well, before we can do an unknown curve, we're going to start with a known curve. So what I'd like you to do is I'd like you to graph y is equal to x squared on all three of these graphs. Notice that this one's counting by 5s, and on this axis it's counting by 1s. I know that it is lopsided, but I did it in order that we would be able to draw on it easier. So I already have my graphs, and the bottom line is that you can't perfectly do this problem in the method that we're going to use it. We're going to do an approximation. And the way I'm going to do that is I'm going to draw rectangles. I'm going to do them using the left-hand value. So if I start on the left of a rectangle that's this wide, I actually don't have a rectangle at all. But on this next one, I'm going to start on this left side, so the left side is touching the curve, and I'm going to go right across, and I've made a rectangle. Now I'm going to start on this one and make a rectangle. And then I'm going to start here, and I'm going to make a rectangle. And this area is going to be my estimate. Hopefully at least one of you is going, Mrs. Shaffer, that is a terrible estimate. It is. It way underestimates the curve. Of course, if I were to make enough of them, and I really don't want you to do this because it would clutter your graph. But do think about it. I'm just showing you a concept with just a few rectangles. If I were to actually do a whole bunch of rectangles, would my estimate actually be that wrong? No, not at all. So it's only because I'm choosing only to make 4, but think about it. If I made all those little rectangles, always with it starting on the left, touching the curve on the left portion of the rectangle and going across, it would actually be a pretty good rectangle. But I have zero desire to do that much work. So we're going to just do it with these 4 rectangles, which actually ends up only being 3 because the first one has an area of 0. So the area of the 4 rectangles is 0. And this one is a 1 by 1. And this one is a 1 by, where are we up at 4 there, right? So 1 by 4. And this one, I'll just write it here for you. Make sure that you are following me. And this one is a 1 by 9. So according to this, the area is 14, the area under the curve. But of course, we know that this grossly underestimates the actual area. So then there's also something called right rectangular approximation method. This is actually almost the same, except that when you go to draw your rectangles, we're still just going to do 4. So I'm going to break my section down into 4 spaces. It says we're going from 0 to 4. I'm just going to do 4 rectangles. Now, the top of your rectangle is going to be guided by the right-hand side of the rectangle touching the curve. So I'm going to make a rectangle where this side is what determines where the rectangle goes. So it's going to go like that. And on rectangle, this one right here, I'm going to go across. So I actually have to extend my left-hand side just to match it. There we go. Of course, now the problem is that this one grossly overestimates the actual area, but we're still going to find the area. This first one is 1 by 1. This next one is 1 by 4. This next one is 1 by 9. Okay, that's where I'm getting these. And the last one is 1 by 16. If I add up these areas, so that's an area of 16, this is an area of 9, this is an area of 4, and this is an area of 1. If I add them all together, I get an area of 30. Neither one of these methods are very good. But eventually, somebody said, I know, I'm still only going to do 4 rectangles. How can you do only 4 rectangles and actually have a stunningly awesome estimate? You can make the height of the rectangle at the midpoint. So I'm actually going to go to 3.5, which is actually in between these two. I'm going to go to 3.5, and I'm going to go up to whatever the y value is at 3.5. So f of 3.5. And I'm going to do it that way. And look what happens when I do that. I overestimate a little bit, but I also miss this part, and they kind of cancel each other out. So obviously this method is awesome, except that this area is a little harder to figure out. It's still 1 on the bottom. From 3 to 4 is still a distance of 1. But what's its height? Its height is whatever the function is at the halfway point at 3.5. So you have to do 3.5 squared. Let's see if I wrote that down. I didn't. 3.5 squared is 12.25. So this is a 1 by 12.25, which of course is just 12.25. Okay, for this one, so I'm going to go over to 2.5, and I'm not going to make a new line. I'm just marking the center so that I can determine how high I want my rectangle to be. So that point right there is the function at 2.5. And 2.5 times 2.5 is 6.25. So this area is 1 by 6.25. Okay, are you with me? This next one, 1.5. And what is the function at 1.5? It's 2.25. Is this more work? Oh yeah, these were easy. These points were right on it, and I could see it at 4. It's up at 16. That's easy. But this is a little bit harder, but it's so much more accurate. So this area is 1 by 2.25. And the last one, you have to find the function at 0.5. 0.5 times 0.5 is 0.25. So it's a 1 by 0.25. This is actually easier than you think to add up because there are 4 0.25s, which makes a whole. So we have 8, 12 is 21. Which makes sense. It's somewhere in the middle. But notice it is not the average. Okay? MRAM is not the average. So be really careful. It'd be very tempting to just do LRAM and RRAM and add them together. But 14 plus 30 is 34. So 44. So you'd get 22. So it's not exactly the same number. Just in case you're curious, the actual exact answer is 21.3 repeating. So this is an amazingly good approximation. If you, and you will before the end of the class, know how to make the exact answer, then this area in blue is 21.3 repeating. All right, let's do another one. Oh, just so you know, and the notes are right down there. LRAM uses the left-hand values of y, RRAM uses the right-hand values, and MRAM uses the midpoint. So I've already drawn them, so you might want to pause the video and draw them yourself. The first thing I do is I make my rectangles. If you're taking the AP exam, they will tell you how many rectangles they want. So they're never going to give you that many. The goal is not to give you busy work, it's to make sure you understand it. So we're going to do 1, 2, 3, 4 sections again, and they each have a width of 1. Okay. It doesn't matter if you do MRAM, RRAM, or LRAM. You still can draw the rectangles the same, and that's important. You can make these lines first before you even know which one you're going to do. So we'll go ahead and we'll do LRAM first. The key to doing LRAM is to realize that you need to be touching the curve on the left-hand side. So in this rectangle, this is the left-hand side. That's the one that needs to touch the curve. That's my rectangle. On this one, in this space, this is the left-hand side, and it's touching the curve, the blue curve right there. This is my rectangle. For this one, this is the left-hand side. I'm touching the curve. Okay. And I just realized that some of you might be able to do this now without me. And in case you want to fast forward, the 3 answers are 10, 13, and 18. And the real answer is 13 1/3. So again, MRAM is an excellent approximation. This is the actual answer. But I am gonna go through it. In this 4th rectangle, I go to the left-hand side, I go up until I reach the curve, and that's how big I make it. Notice that it's now a mix of underestimating and overestimating. So LRAM does not always mean underestimate, just because it did on the first example. It means you touch on the left. So this is a 1 by 2. This is a 1 by 1. This is a 1 by 2. And this is a 1 by 5. That gives me an answer of 10. MRAM. MRAM means I go to the center and I have to do a lot more work. I need to know how high that rectangle is. And since I'm basing it off of 0.5, I need to do 0.5 squared, which is 0.25 plus 1. So the height is 1.25, which is f of negative 0.5. So I'm at negative 0.5. I squared it, and I added 1. For this one, I'm going to go to 0.5, and I'm going to go up, which of course is going to be the same. So this area is 1 by 1.25. This one is 1 by 1.25. This one, I go to 1.5, and I go up, and I make my rectangle. So what is f of 1.25? Sorry, I'm running out of room. But f of 1.25, allow me to get out my calculator. I don't know off the top of my head. 1.25. Oh, sorry, not 1.25. 1.5. Thinking that didn't sound right, which I do know off the top of my head. Which is 2.25 plus 1, so 3.25. Does that look right? 1, 2, 3.25, definitely. 3.25. But since it's times 1, it's just 3.25. And last one is 1 by, now I'm going to go up to 2.25, which is 6.25 plus 1, 7.25. Again, there's 4.25s, which makes it easy. This is 10, 11, 12, 13 is the answer. Last one. So I go to each rectangle and I go to the right. And on the right-hand side, I make a line across. I look at this rectangle, I go to the right, I make a line across. I look at this rectangle, I go to the right-hand side, I make a line across. I go to this rectangle, I go to the right-hand side, I go up until I reach the curve, and I go across. This one's going to go much faster because you don't actually need the formula. You can use it at 3. 3 squared plus 1 is 10, but I can also just look at my graph. So this is a 1 by 10. This is a 1 by 5. This is a 1 by 2. And this is a 1 by 1. So what does that give me? 1 plus 2 plus 5 plus 10 is 18. Okay, and this one overestimated on everything but the last one. It was a little bit of an underestimate there. And that's LRAM, MRAM, and RRAM. I need to make a quick note to AP students. So on AP, they're really fussy about the way they want this shown, which I only learned because I was a grader and I found it very distressing. This last one that I did would actually be acceptable because I have a combination of multiplication and addition. But on this one, do you see how I only show the addition? I actually wouldn't get credit for that. You have to show both multiplication, even if it's obvious, and addition in order to get credit for LRAM, RRAM, and MRAM. Multiplication and addition. So also for me on my quizzes and tests, I will not give you credit without it because I do not want you to know how to do this and lose the point on the exam just because you didn't show your work correctly. Next one. Find the area between the x-axis and the curve y is equal to negative x squared plus 2x plus 24. So you're required to make a good sketch. You can't do this without the sketch. So I look at this. I know it's going to be a downward parabola. It's going to have a y-intercept of 24. So 0, 24. I personally am going to factor out the negative because it'll make it easier for me to factor it. Super easy, actually. Now I know it's going to be x and x. It's going to be 4 and 6. The 6 is negative. So now I know its x-intercepts are 6, 0, and negative 4, 0. So here's my sketch. I'm just making a sketch. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it's going to go from there to there. And then it's going to be up here at 24. Notice I didn't actually count those. I want to do the ones on the x-axis because that's going to mark my rectangles, but here I just need the height. Now that's actually not the vertex because this is 10 across. Then at 5, so 1, 2, 3, 4, 5, this is where the vertex is going to be. So it looks something like that. Wow, that's so bad. It'll have to do. No, it's too bad. I can't do it. So I think I'm going to make my parabola first. Here's my axis of symmetry. Yeah, that's much better. And now I'll fill in numbers. So there's 24. What is it if I put in a 1? Well, before I do that, let's make sure that I need it. I want 5 rectangles, and there are 10 sections. So 5 rectangles, 10 sections, 10 sections means that they're each going to be 2 wide. So I go over 2 and I draw a line up, over 2 and I draw a line up. So, aha, do I even need the vertex? I don't. I don't actually care what that point is. So I'm going to erase that line. It just helped me draw it. All right. And then, so I need this one and this one. 1, 2, 3, 4, 5. Right? I am going to do MRAM. So what's weird is I'm going to go in between, and I actually want this point right there. That's going to be my rectangle. And then from here, I go to here, and that's going to be my rectangle. Oh, I am going to use the vertex after all, right? And then on this one, I go to here, and I go across, and then I go here, and I go across. So each one of these is going to be a 2 by, so 2 by something, plus 2 by something. There's 5 of them, and they all have a width of 2. And this just is supposed to help you remember AP that you have to show both addition and multiplication. So how high is this? Well, since I'm at 1, 2, 3, 4, 5, this height is the function, the y value at 5. So negative 25 plus 10 plus 24 is 9. So that last rectangle is 18. This next one is f of 3, which is negative 9 plus 6 plus 24, which is 21. This next one is f of 1, which is negative 1 plus 2 plus 24, which is 25. So this rectangle is 25 high and 2 across, so it's a 2 by 25 rectangle. Now it is a parabola, so this should be symmetrical. I'd be plugging in a negative 1. So f of negative 1 is negative 1 squared is 1, but there's still a negative there. So negative 1, 2 times negative 1 is negative 2, plus 24 is indeed 21. So I won't do the last one. I can see that it's going to be 9. So this is a 2 by 9. This was a 2 by 21. 2 by 25, 2 by 21, 2 by 9. And my final answer is 170. Okay, so that's how you would do MRAM. So a lot of times you'll have something that's 10 intervals wide in order to only do 5 rectangles, and that way MRAM is easier. All right, let's do an actual word problem for these. The table below shows the velocity of a model train engine moving along a track for 10 seconds. Estimate the distance traveled by the engine using MRAM over 5 subintervals. So again, that combination where you have 10 seconds long but only 5 subintervals will make it easier to do. So you only need 5 rectangles. So I am going to mark this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But in the other direction, I kind of just glance and I say I need to get up to 22. So I think about the fact that that's how high I want this to be. So this is somewhere around 10. This is somewhere around 20. But otherwise, I do not try and make an accurate sketch. So I start off at 0. I go up to 12. At 2, I go up to 22. And that's all I do. I just put the number on top. 3 is down here at 10. 4 is down here at 5. 5 is up here at 13. 6 is 11. 7 is 6. So comparatively, I just wanted to make the 6 a little higher than the 5. At 8, I'm at 2. At 9, I'm back up at 6. And at 10, the train has stopped and it's 0. So look what this little engine does. This little train takes off like a shot. It's got so much energy in the beginning. It works its way all the way up to 22 inches every second. But then it starts to slow down. I don't know if it hit a curve or what, and then it gains some speed again. Look at it go. And then that was its path. So it had, I don't know if you've ever seen one of those little trains. They definitely seem to chug and then they get a little spurt of energy. So I want to know how far it went. So keep in mind that distance is equal to rate times time. That's what this graph is. This is a graph of my velocity or my rate over time. So on our thing that was just going straight 75 miles per hour, if I wanted to know how far it went between 7 o'clock and 9 o'clock, the area under the curve gave me rate times time. I'm going to do that exact same process, except I want to know the area under this squiggly thing. Well, you can't do that. So the area under the squiggle, instead, we're going to break it down into rectangles. Now, fortunately, only 5. So you're going to love this because there's no function. There's just data. Data is better because now watch. This is already given to me how high that one in the middle is for MRAM. So this is a 2 by 12 rectangle. So it's going to be 24. This one is a 2 by 10. So 20. This one goes all the way up to here. So this one's hard to draw because you have to extend the sides. It's above its two sides. So this is a 2 by 13, which is 26. This is a 2 by 6, which is 12. And this is also a 2 by 6. So look how different it is. On this one, had a nice overestimate and underestimate. On this one, it's completely off, but we still have to write 12. So we'll go ahead and we'll add those up. 24 plus 20 plus 26 plus 12 is 94. What is the unit? Since we are doing rate in inches per second times time, so velocity times time, in seconds, we're left with inches, which is a double line. Okay, everybody, last one. Oil is leaking out of a tanker damaged at sea. The damage to the tanker is worsening as evidenced by the increased leakage each hour, recorded in the table below. Give an upper and lower estimate of the total quantity of oil that has escaped after 8 hours. So like we did with the last ones, I do need to make it into a graph. 1, 2, 3, 4, 5, 6, 7, 8. And it doesn't need to be perfectly marked on this side, which is in gallons per hour. I just really want to record the basic shape of it. So if it's 0, it's at 50. And then 1, it's at 70. It goes up to 97, 136, 190, 265, 369, 516, and 720. So when it says an upper and a lower estimate, we know that the graph looks something like that. The area under the curve would give us the exact amount. But we can't find that area because we don't have the function. But we can make all of these intervals. So if we did LRAM, we would be underestimating the actual answer, which would be a lower estimate. If we do RRAM, we'll be overestimating. So we're going to do both to see what we get. In each case, the interval is just 1. So for LRAM, the rectangles are easy to figure out. This first one is 1 times 50. And then 1 times 70. Okay. Obviously, it's silly to keep writing times 1, right? I only am showing that for AP, where they require that you have both the multiplication and the addition. But what you do need to pay attention to is the fact that this is not going to go all the way up. Sometimes people are just a little bit lazy and they just write all the numbers. 369 plus 516 plus 720, but you can't do that because there actually is no rectangle using the 720. The last rectangle you make for LRAM is going to be the one that has a height of 516. So be really careful there that that is not one of them. If you do all this addition, let's see, what do you get? 1693. So let's talk about the units for a minute. When I first introduced this concept, I talked about how distance is equal to rate times time, which of course we call rate of velocity. So velocity times time. So if you have the velocity, then the velocity times the time will give you the area under the curve, if it's rectangular. And that works because if you have something like miles per hour times hour, you will get miles. In this case, we have a rate times time, but ours is gallons per hour times hour. So when you do that, you don't get a distance, you get gallons, you get an amount. So this is going to be 1,693 gallons. Now for RRAM, if you came in from this direction, what number would now be eliminated? Instead of the 720, you do have a 1 by 720 rectangle, but you wouldn't have a 50. So this end would be missing. So RRAM would be 70 plus 97 plus 136 plus 190 plus 265 plus 369 plus 516 plus 720, but not the 50 because we're using RRAM this time. And that answer will come out to be 2,363. So you might be thinking, how come we didn't use MRAM again? Because it was such a more valuable answer. Well, this is one way that they can give different lower estimates and higher estimates. So a scientist could sit there and say, oh, it's possible that it's just, this graph is going up and then it goes up to the next one and it goes up to the next one. So maybe that LRAM is good. Maybe it's only lost 1,693 gallons of oil, where somebody's like, no, we really need the worst case scenario. All right, well, the worst case scenario is that it reached that 70 almost right away, right? And then it reached that 97 almost right away, and the upper estimate is true. So there really could be almost 2,363 gallons of oil spilled. So does it make a difference? Absolutely. So now, once it reached 720 gallons per hour, it's not losing any greater speed after that point. It just stays at 720. So maybe a hole was created and kept getting bigger and bigger, but but now the hole is stabilized and it's losing at exactly 720 gallons per hour. So if the tank contains a total of 25,000 of gallons of oil, how many more hours will elapse in the worst case before all the oil has leaked, or in the best case? So how do we figure that out? Well, let's take our 25,000 gallons and say, okay, first 8 hours, we've already lost 2,363. Then you can say that is, let's see. I didn't do that one. So we take our 25,000 and we subtract the 1,693 that have already been for sure let out, because that's the least possible amount. That gives us 23,307. And now I'm going to say 23,307 divided by 720 gallons. That'll tell me that there's about 32.37 hours left. So AP and honors, but specifically in AP, because you will lose a point for this, sometimes it's super easy to sit there and say, okay, first I'm going to subtract. That's how many gallons are left, or that's how many gallons are left over this many per hour. Notice these two statements are not equal to each other. It's very easy to do a subtraction, get an answer, and then want to do something to that answer. But this side and this side are not equal. They will dock you for that mistake. You can't let that happen. So if you want to do your subtraction and then you decide you want to divide by 720, that's great. Just make sure you also divide this side by 720. But either way, it's going to come out to be 32.37 hours. The question is this the worst case scenario or the best case scenario? It depends on how you're looking at it. If you're looking at it that you hope not that much has leaked out yet and you still have time to stop the flow, you might sit there and say, oh, there's still 32 hours left. We have enough time to try and stop this from getting much worse. The best case scenario, or it might just be, let's just get it all done and start the cleanup. These are the decisions that people have to make in the real world. Do we even have enough time to start trying to stop this problem? Or, oh, it's only going to be 32 hours. We might as well just start bringing in all the cleanup equipment. So that's why this math is important. In order to do the other one with using the RRAM, you would do the same thing, minus 2,363, and divide that by 720, and then you would get 31.44 hours. So again, which one is worse? Well, if you're hoping to have time to get somebody in there to repair it, this one seems better. Got a little bit more time, but probably not enough to make a difference. All right, that is it for RAM, and I hope you have a great day.